Hello to all participants of Cosmology from Home 2024. My name is Silvia Manconi. I am a Marie Curie Fellow at l'Arche in Nancy, in France. And in this video, I'm going to present to you an overview on astroparticle physics. I will start this talk with an introduction, and then I will move to discuss two selected topics from my own research. The first one being antimatter in cosmic rays, and the second one, the galactic-center excess. I will then conclude with an outlook, and just in the slides, I've been inserting some more highlights I could not cover in the main talk, but I thought that were interesting for this audience. So let's start with the introduction. And the definition of astroparticle physics is, in general, considered as all the physics we can learn studying messengers produced in astrophysical environments. And those messengers in modern astroparticle physics are gamma rays, photons at different energies, neutrinos, cosmic rays, and also gravitational waves. So as you can see, in this definition, we end up putting a wide umbrella of interconnected topics, and the boundaries between particle physics, astrophysics, cosmologies, and astroparticle physics are indeed very blurred, as is very evident from the white paper that the European Consortium for Astroparticle Physics has been put out in the recent years. So following a bit the theme of this year Cosmology from Home, in astroparticle physics, from one side, we need observations and theory, really 6 observations, because we want to answer to the question, are the signals in the astroparticles that we observe from physics beyond the standard model, for example, from dark matter? And on the other hand, observations seek theory, because they ask us, do we understand the properties of the astroparticles that we observe? And just to start introducing the observations of astroparticles, let's have a look to the main astroparticle messengers. On this left plot, you see a modern collection of the observation of charged cosmic rays and neutrinos. This is a flux as a function of the energy. And you see different entries in this plot that are coming from a plethora of precise observations from different detectors in space and also in the ground. So the spectrum in general is looking at a power law with some structures that are known as the knee and the ankle. In this talk, we are going to concentrate on the part at lower energies than the knee, which is considered to be of galactic origin. And you see that in this region, the flux is dominated by proton components. Then we have some electrons and positrons and antiprotons. In the same plot, I've been also inserting the neutrino flux. This is the diffuse neutrino flux that is observed by the ice cube detector. Those charged particles, both in their original sources and also through diffuse processes in our Milky Way and beyond, produce a spectrum of multi-wavelength photons going from the lowest energies, from radio emission up to X-rays and gamma ray emissions. And as I was saying, to this family picture, not only charged cosmic rays, neutrinos, and multi-wavelength photons should be added, but also in the modern multi-messenger astroparticle physics, also gravitational waves addition are the key. And I thought that this was useful for this audience because we are looking to different scales in our universe with different astroparticle and cosmology observations. From the point of view of the astroparticles we are going to concentrate on in this talk, the horizon is pretty small. And mostly this is because charged particles are confined by magnetic fields up to 10 to the 6 GeV in our galaxy. So if we are observing charged particles with our detectors up to 10 to the 6 GeV, those particles, we are pretty sure they are coming from our own galaxy, from sources and diffuse processes happening in our own galaxies. If we look to extragalactic sources, then the horizon is not as large compared to cosmological observations. And specifically, this is what I'm representing in this plot. So here you see the horizon in megaparsec as a function of the energy of the astroparticle messengers that we are looking at in GeV. And let's concentrate on the red line, which is for protons. This line is saying to us that everything above is not observable. And the reason is that high energy protons interact with photons in the cosmic background radiation, for example, with the CMB, and with the phenomenon known as the JK cutoff, we cannot observe charged particles, protons, which are coming from distances larger than 200 megapulsars. So this is the horizon for charged cosmic rays. This is not true for neutrinos, so neutrino can explore more deeply into our galaxy and beyond. And looking to the high energy gamma rays, the horizon is even more limited, and specifically at those energies at 10 to the 6, we are limited to observe a bit farther than the Milky Way, and this is because of different mechanisms of absorption of gamma rays with interactions with the cosmic background radiation. And specifically, this is named as the extragalactic background line absorption. So those two dashed shaded area are not observables with astroparticles that are gamma rays and protons. And as I said in this talk, I'm going to concentrate on GeV charged particles that are even confined to lower redshift in our universe. But nevertheless, even if we are looking to the local galaxy, there are close connections of this part of astroparticle physics with particles cosmology, for example, because every new particle or interaction that we discover at the level of a galaxy might have interactions and effect with the thermal history of the universe, affect observable effects in the CMB and in the clustering of matter at different scales in our universe. And in general, if we are seeking for new particles that could be or not dark matter candidates, the complementarity of different new physics searches is fundamental. So indirect searches at the galactic scale and the extragalactic scale are really complementary with respect to the direct and collider searches, because they test different properties of possible candidates for being, for example, the dark matter in our universe. So bear with me. From now on, I'm going to look at redshift about 10 to the minus 6. And this is a representation, a sketch of the journey of astroparticles in this volume in the universe, in our galaxy. And in this sketch, you see in gray the dark matter halo. So we believe that our Milky Way is embedded in a dark matter halo, which is peaked at the center. And here we are with our detectors observing astroparticles. We believe that if dark matter, for example, is made by new particle, those particles can interact, annihilate, and decay, and produce different astroparticles in their final states: photons, electrons, positrons, or antiprotons, for example. The same is true if dark matter is made by new compact objects, such as primordial black holes. We expect that through the phenomena of Hawking evaporation, they can also be sources of astroparticles in our galaxy, producing again photons, electrons and positrons, and antiprotons. And also, other new phenomena, for example, the existence of axionar particles and QCD actions, for example, they can produce again photons, for example, because they decay into photons in our galaxy. And if those particles make up a significant part of the dark matter in our galaxy, this signal is expected to have similar properties with respect to other observables in dark matter searches. Not only dark matter can emit astroparticles, but the majority of the astroparticles that we observe are actually produced by different very high energy astrophysical sources, such as, for example, supernova and the explosions that accelerate with shock waves the particles that they meet in the interstellar medium, and those particles then can again interact with the interstellar magnetic fields, with the interstellar medium, with the photon fields coming from different radiations, such as the stellar light or infrared background, and produce again astroparticles, electron positrons, protons, antiprotons, and photons at different energies. Those particles being then produced by new physics phenomena such as dark matter, or being produced by our astrophysical sources, will be transported in our galaxy, and depending on their charge, on their mass, on their energy, they will be affected by different mechanisms. For example, we know that the inhomogeneities of the magnetic field in our galaxy cause a transport that is diffusive in nature, and so we need to take into account this if we want to model the transport of those astroparticles in our galaxy, but also they will be emitting photons at different energies through energy loss processes, for example, and so on. And not only this, but imagine that we have a standard astrophysical source that is emitting photons. If, for example, there are axions in our galaxy, those actions can convert photons and absorb and gives us some features in the spectrum of photons coming from astrophysical sources. So all those signatures coming from exotic sources and astrophysical sources are then integrated together in the observations that we have. And what are the current state-of-the-art detectors? At the moment, we have different satellites in space that can measure the flux of astroparticles. The most important being for this talk, the Alpha Magnetic Spectrometer, AMSO2, which is on board on the International Space Station. And this is very important for us in this talk because it's the only detector at the moment that can distinguish particles from antiparticles with a magnetic field on board and give to us % precision of the charged cosmic ray measurement from the GeV to the TeV energy range. From the point of view of photons, this is an overview of the sensitivity of current detectors and in dashed line future detectors. You see that we have different detectors in the X-ray regime, and then we have different detectors here at the GeV and in the TeV energy range. The most important one for this talk will be the Fermi-Lot detector that is now taking data since 15 years and is giving to us an important sensitivity in the full sky gamma ray emission. And here you see another family, a portrait of the gamma ray telescopes at the moment in operation with the CTA addition that is going to be the gamma ray instrument of the next decade. And you see that we can cover from the GeV to the TeV energy range with these different detectors. What are the observables that those detectors deliver to us? Well, we know already from the previous plot that we measure the local fluxes of charged cosmic rays. And here you see a zoom in of these local fluxes. Again, we see that this flux is dominated by protons. Then we have electrons, positrons, and antiprotons. And those high precision data are all from the AMSO2 detectors, the one with the lowest errors. Not only we can measure the local fluxes, but experiments such as TBET and IceCube that collect a lot of statistics for cosmic rays, they can also give to us information of the spatial distribution of arrival directions of those charged particles. Charged particles, because they are diffused in the galactic magnetic field, they don't point directly to their original astroparticle source, but still, in a diffusive regime, we expect if we have a significant inhomogeneity in the distribution of the sources to be able to observe some anisotropies in the observed flux. And this is indeed something that is observed. We have a dipole anisotropy and also smaller scales anisotropy observed, but this is not going to be touched in my talk, unfortunately, because of time. And from the point of view of the multi-wavelength photons that those charged particles emit, as I said before, we expect diffuse emission coming at different wavelengths. For example, we expect radio emission coming from charged particles interacting with synchrotron radiation in the galactic magnetic field, and then gamma rays coming from the interaction of protons and electrons with the interstellar medium and the photon fields. And recently, also a diffuse emission into the neutrino flux has been detected by the IceCube collaboration. Not only we have this large-scale diffuse emission, but some experiments, for example, in this family portrait, the one that you see here, OC and S, can really resolve deeply into the small-scale properties of specific sources and give to us a morphological information on how the gamma rays, for example, around the cosmic ray sources are looking like. And this is an example that we are going to see later on. Those sources and the properties are typically collected into catalogs. So the collection of all those observables and the connection of those observables in a multi-messenger and multi-wavelength strategy is the key to understand the properties of the astroparticles that we observe. And let's now do the exercise of imagine that we have an observed astroparticle flux, whatever it is being, can be charged particles, can be gamma rays, and we want to, I'm sorry, understand if there are possible signatures of dark matter interactions. For example, GeV dark matter, we can interact in massive particles. What are the signatures that we expect to observe in, for example, the local flux of those particles? We typically expect that the particles that are produced from dark matter annihilation or decay will be summing up to the ones that are produced by standard astrophysical processes and cause spectral distortions on exaflops of cosmic radiations in a specific energy range and with specific properties. In particular, the level at which those spectral distortions are arising are giving to us information on what is the interaction strength of dark matter, for example, the annihilation cross-section of particle dark matter. The shape, the spectral shape of the signal is giving to us information on the annihilation channel, for example, of those dark matter particles, and the cutoff energy at which we finish to see the spectral distortions is giving to us information of the particle dark matter mass. And this is a very important strength of seeking for indirect signatures of new particles and dark matter particles, for example, with astroparticle messengers, because what we observe can be directly connected to the fundamental properties of the new particles and the new interaction that we are seeking. This is true if we understand very well the astrophysical background and we can extract and subtract the astrophysical background on top of this signal from the observation, which unfortunately sometimes is not the case, as we are going to see in our topics. So how we can constrain the huge space of particle dark matter, and not only particle dark matter hypotheses that are at the moment in the market. So from the ultralight dark matter to compact objects such as primordial black holes, we have a different complementary way of using astroparticles to constrain those theories. The standard paradigm of using astroparticles has been for the last decade to use those astroparticle observations to constrain mostly GeV scale particle dark matter, but recently, and as it was covered very well again in the EUCAP white paper, not only with those astroparticles we can constrain GeV particle dark matter, but we are extending also our constraining power to different types of hypotheses. For example, we can search for primordial black hole signals into the different astroparticle spectra, but we can also look for lighter dark matter particles in radio observations and also X-rays and gamma rays through their interactions with photons. So the indirect dark matter searches are really diverse, and in this scheme you just see in green a general overview of what are the different observables, astroparticle observables, but not only, also the cosmological as the CMB, and we are really having different important opportunities with the current precision data. And this data precision not only gives to us important opportunities to test different dark matter hypotheses, but is also challenging our current theoretical understanding, not only of the new physics that we are seeking, but also on the standard astrophysical processes that produce our background. And in this slide, I've been just collecting some timely questions that we have from charged cosmic rays and diffuse background emission physics. From what concerns the charged cosmic ray spectrum that I showed to you before, the main sources of this spectrum are not yet completely settled. Supernova and supernova remnants are for sure the most important historical candidates, but they have been recently considered together also with other possible accelerators in our galaxy, for example, compact star clusters that have been found through multi-wavelength analysis to actually have a significant cosmic ray density. Then, from the point of view of the theoretical understanding of the transport and the acceleration, we still need to understand what is the maximum energy that the different sources can accelerate, and if this maximum energy is enough in order to explain the maximum energy of the charged particles that we observe. And also the microphysics of this acceleration process is still a subject of active investigation through, for example, particle in cell simulations. Also, the galactic scale, so the global transport of charged particles in our Milky Way, there are many opportunities to develop our theories because the microphysics of this transport process is yet to be completely understood. And also recently, the mechanism of transport of cosmic rays around their sources has been gaining more and more attention because this can importantly change the shape of the astroparticles that are injected into the interstellar medium. From what concerns the diffuse background emissions, going from the GeV gamma rays, we still need to settle the composition of those background emissions. And recently, has been claimed that a dipole in the diffuse gamma ray background is present that is consistent with the dipole that we see in charged cosmic rays. And this might point to a similar origin of those two emissions. So this is very interesting and a subject of active investigation. we have been detecting recently PV gamma rays, and the idea is that we don't yet know if those sources of PV photons are leptonic or hadronic, and different theories are under investigations. And then I've been mentioning to you that we observe neutrinos, both galactic and also point-like sources, but the origin and what is the class of sources in our galaxy that can produce the neutrinos that we are observing with those characteristics is again under investigation. So in this plot, I've been reproducing the collection of the observation of the diffuse background emission from the gamma rays, the neutrinos, and the ultra high energy cosmic rays as well. And one important puzzle still to be unveiled is why those different emissions have a similar flux scale at different energies. So this is pointing to possibly a similar origin, but the space is open for investigation. And those questions that not only involve, again, the new physics sources that I've been mentioning, but also what we call the background astrophysics in new physics sources. But this is all involving major interest questions for astrophysics. So the synergy between the astroparticle theories working on cosmic ray theory, diffuse background emission theory, and the ones working on new physics sources is really fundamental to make progress in the next decade. And this is going to be even more clear after, I hope, I will discuss with you the two selected topics I decided to include in this talk. Because when theory meets the precise observations of astroparticles that we have often what we call in our field excesses, not tension. And those excesses, they really challenge our understanding of galactic cosmic radiation, and they hint at new processes, as I was saying before, being them exotic of astrophysical. And the two excesses I'm going to discuss in this video are the AMSO2 positron excess and the Fermi-Lat gamma ray galactic-center excess. Those are not the only one in the astroparticle community, and you can have a look to this SNOMAS paper for a recent discussion of the main puzzles in astroparticle physics and for some guideline for the future to how to solve them. Let's start with antimatter in cosmic rays. And first, let's answer to the question why, at first place, we want to look to antimatter signal in the galactic cosmic rays flux. In principle, there are matter annihilations that annihilate into different final states, for example, hadronic or leptonic, will produce in a similar amount of particles and antiparticles. But since antiparticles in the local cosmic ray flux have already a lower flux with respect to particles, for example, there is about 1 antiproton every 10 to the 4 protons, or 1 positron every 10 to the 1 to the 2 electrons. The game that I was showing to you before with the sketch in which we search for a spectral distortion on top of an astrophysical background should be easier because I'm going to fight with a smaller background. And also I'm going to be sensitive to smaller couplings that are really modeling the normalization of the signal that I expect. And then in principle, this is caused by the fact that astrophysical processes produce a lower background of antiparticles, because in the standard scenario, we expect antiparticles to be created primarily by the spallation of primary cosmic rays. So supernova remnant should produce protons. Those protons interact with the gas in the interstellar medium and with different processes that can produce electrons and positrons in different amounts. This is a flux, a guaranteed flux of antiparticles that can be also affected by astrophysical uncertainties, for example, in the interaction cross-section of those particles that are covering energies much larger with respect to the ones that we can measure at colliders at the moment, but still, we expect a lower background in antimatter. I'm going to focus in this talk, as I mentioned before, already on positrons, but I've been inserting in the additional slides I've been mentioning before also some updates on the antiproton, antimatter, dark matter searches, and anti-deuterons and anti-helium news and prospects for the future. So you can have a look. And from all this discussion, you will not be surprised, and I'm sure that you have been hearing about this, that when AMSO2 and before that Pamela experiment measured an increasing flux of positrons as a function of the energy, this was immediately considered as a possible signal of particle dark matter. In this plot, you see In this plot, you see the flux of positrons detected by the EMS2 as a function of the energy. And here I'm overplotting the secondary emission estimation coming from the spallation of primary cosmic rays. And this is an updated computation that we worked out recently, in which propagation and cross-section uncertainties are taken into account. As you can see, even if we take into account the most conservative uncertainties in this astrophysics, we cannot reach the level of the positrons that are observed by AMS2. So this is the positron excess, which is most likely at tens to hundreds of GeV. And initially, this signal has been interpreted as to be a striking evidence for dark matter annihilation. In fact, it's very well fitted by the annihilation of TV scale particle dark matter, and specifically WIMPs, annihilating into leptonic final states. So I've been discovering dark matter in the positron flux. The current agreement is that actually this is not a dark matter signal, but it's rather an astrophysical signal coming from factories of positrons and electrons in our galaxy that are pulsars. And even if we would like to explain all the excess of the positrons with only dark matter, at the moment, this hypothesis is considered very unlikely, because the parameter space of the dark matter mass and the interaction cross-section that could explain the positron excess is already tested and excluded by other indirect sources, for example, the Planck's CMB limits, but also other gamma ray limits. There might be some exotic mechanisms that you can use in order to reconcile all the bounds, but this is pretty fine-tuned. And what if there are local dark matter clouds that are emitting this important flux of positrons? This is again disfavored by cosmological simulations. So at the moment, explaining all the positron excess with dark matter is pretty unlikely. And if we want to explain part of the excess, this is again a possibility. But the fact that we observe a smooth flux with little space for feature is making some trouble for explaining some possible additional spectral distortion coming from the dark matter signal. And then the main argument is that we have some natural astrophysics candidate, but we can still use positrons to put constraints on particle dark matter in this energy range. And the astrophysical sources that are possibly producing the flux of positrons that we observe are pulsars and the nebulae. Pulsars are galactic objects which are fast-rotating magnetized neutron stars that come from the collapse of very massive stars. They have a high magnetic field, and in the particle wind that is extracted from the surface, a cascade of electrons and positron pairs is produced. Those electrons and positrons fill what we call a Bow-Shock nebula, and then at some point, this bubble of electrons and positrons can be released in the interstellar medium after a few kilo years, and those electrons and positrons will propagate in the interstellar medium, reaching our detectors and emitting photons along the way. We have some theory argument also to relate the spin-down luminosity of the pulsar to the particle and electromagnetic energy that is emitted. So from this point of view, pulsars and the nebula are natural candidates from the theoretical point of view, but also from the multi-wavelength evidence data, we have some arguments. If we want to relate what is the pulsar electrons and positron injection to the local flux, we have still some steps to work out, because imagine that we want to write a source term to propagate those particles in the interstellar medium. We need to know what is the energy spectrum that is emitted and what is also the normalization. So typically what we do is to parameterize this with a spectral index and with an efficiency parameter. And those two parameters really rule how much your pulsars can or not explain your positron excess, and how each individual pulsar in our galaxy will contribute or not to the observed flux. So the spectral index is distorting a bit the emission as a function of the energy, and the efficiency of conversion of the spin-down energy into electrons and positron pairs is ruling the normalization. And since electrons and positrons in our galaxy lose energy very quickly, if we want to explain the positron excess that we observe at GeV energies, we really need local sources. And with local, I mean around a few kiloparsecs. If we look to catalogs, we have not so many sources around 1 kiloparsec that could give to us a significant flux. And the question here is now how we can constrain the properties of those possible positron factories in our Milky Way. We need to know what is the efficiency of conversion, and we need to know what is the spectral index of the particles that are emitted. And this is something that we can do with multi-wavelength analysis of the emission around the pulsars. In fact, those electrons and positrons that are accelerated will lose energy by inverse Compton scattering and synchrotron emission and produce a cascade of photons in a broad range of frequency. So by bundling the intensity and distribution of this photon emission, we want to infer the properties of the cosmic rays, positrons and electrons as well, because pulsars produce, we believe, an equal amount of positrons and electrons. And what is this flux that is released in the interstellar medium and is then propagating until our detectors? And we can explore these multi-wavelength photons with the important detectors that we have in the gamma ray regime, from the Fermilab up to the Ock, LASO, and S detectors now, and the Cherenkov telescope array in the future. So a few years ago, a very important detection of a multi-wavelength emission coming from a nearby pulsar has been delivered by specifically the Ock collaboration. And I'm going to discuss now a specific source, which is not having just a full number as many other pulsars, but is having a name. It's called Geminga. And this is because it's the first radio-acquired pulsar that was discovered in gamma rays. This is a very nearby source. So it's checking different boxes for being a possible source of the positron excess that we observe, because it's also pretty hot. So the positrons that have been emitted have the time to propagate until our local observations. And recently, a breakthrough in the observation of pulsars has been the observation of an extended gamma ray halo, which now we detect from GeV to multi-TeV. So this is not only the emission around the specific compact object of the Geminga pulsar, but this is an emission extended tens of parsec around the central pulsar. And we observe this extended emission with Fermilab at energies larger than AGV, with S, with Ock, and with LASO in different energy ranges. This emission was discovered by Ock in 2017 with the associated science paper. We interpret this photon emission as coming from electrons and positrons diffusing away from the nebula, up scattering background photons and producing photons through inverse Compton emission. And again, the scale of this emission is pretty extended around the central pulsar, is tens of parsec. So these objects in the sky are called pulsar halos, sometimes TV halos, also in the community, because they've been discovered in the TV energy range by the Ock experiment. And we are using at the moment those halos, and specifically the halo of Geminga, which was the first one that we discovered, as magnifiers in order to understand the properties of cosmic electrons and positrons. In the left plot, you see an updated collection of all the measurements of the emission coming from the Geminga halo. We have here the emission discovered by Ock, the S and Fermilab gamma ray emission that we can model with a model of electrons and positrons that have been produced by the Geminga pulsar and are diffusing away from the pulsar. And then recently we have been looking to X-rays to try to put constraints of the local magnetic field at the position of the halo. And all in all, those multi-wavelength observations allow us to constrain the efficiency of conversion of the pulsar spin down into electrons and positron pairs in this specific source, and also to understand a bit better what is the transport mechanism around the source in order to model better the diffusion around the source. And this is saying to us that the diffusion properties around pulsars look very different with respect to the average galactic properties, and in particular, the diffusion is suppressed with respect to the mid-galaxy. With those constraints, we were able to constrain much more the possible contribution to the source, to the positron excess, and finding that, including uncertainties in the transport, in the spectral parameters, and efficiency properties that are still there looking to the data, and often are also degenerate, we still can conclude that Geminga can contribute to the local AMSO2 flux at the TV level, but cannot explain all the positron excess. But the pulsar that I've been discussing to you is not the only pulsar that we have in the galaxy. If you want to know more about this topic, I've been collecting some references for a review talk I've done last year in this bibliography. So I invite you to have a look. So I said that to you that Geminga is not the only pulsar in the galaxy, and now the game is to understand if a galactic pulsar population can explain positron excess. And the answer, coming from attempts from my group, but also some complementary attempts from other groups, is yes. If we simulate a population of pulsars looking similarly to what we observe in the Geminga pulsar, with emission that we see tuned on multi-wavelength data, indeed, we can explain the level of the positron excess. And this has been done with Monte Carlo simulation, and this is what I'm inserting in this plot, but also with catalog sources. And we end up concluding that few nearby bright sources can indeed explain the positron excess together with the mean gap. To move forward in this, we need better understanding of the secondary emission, and this is something that we have been delivering recently with state-of-the-art propagation and cross-section implementations. And the secondary emission is this decreasing emission that we see here that still can contribute significantly, depending on the energy, to the positron flux. And then the next step is to inspect the catalog to select the pulsars that are most likely contribute to the positron excess and go to gamma rays telescope to constrain their properties in electrons and positrons emission. This pulsar halo population is extending now from the KV to the TV and will allow to us to understand the properties of emitted positrons, but also to have a more extended theoretical understanding of the transport properties around the sources. And indeed, the observation is going to have a bright future on this field, because for the moment we just have 3 confirmed halos in our galaxy, but there might be more pulsar halos already in catalogs that have been assigned the pulsar with nebula label. And with forthcoming observations, for example, from the CTA, we expect to have finally a population study to constrain the properties of those sources. Although in X-rays, we need a large field of view for nearby objects, so it might be rather be better to look to far away objects to constrain the population. I'm now going to discuss the galactic-center excess. This map is representing the photons that we observe from the Fermi lattice experiment. This is a counts map, so where you see red and yellow are brighter spots in our galaxy and beyond. And in the data from the Fermi lattice experiment since 2009, so the first years of data, a statistically significant excess has been detected. This is making up a few percent of the inner galaxy flux, so the flux that we observe around few degrees around the galactic center, and has been significantly detected by independent analysis over the last 14 years. This is an excess with respect to what? In this map, we have a complicated structure of different sources. In general, we can distinguish the sources of gamma rays in 2 broad classes: diffuse emissions and astrophysical sources, as I was explained to you before. And the galactic diffuse emission, which is the bright emission that you see in the plane in this plot, is coming from the cosmic ray interacting with the gas in radiation field through, for example, Weierstrass emission, pion decay, or inverse Compton scattering, while the spots that you can see are compact individual sources in our galaxy or faraway objects such as blazars, which are galaxies having important jets pointing in the direction of our observations. Those 2 classes of sources are affected by different uncertainties. The diffuse emission is having a lot of systematics, because in order to produce a model to explain what we observe, we need to understand, for example, the distribution of gas in our Milky Way or the properties of the galactic magnetic field. And from the point of view of the astrophysical sources, we cannot detect all of them, but we will be at some point blind to faint unresolved sources that can contribute with some diffuse emission to our field of view. So this excess that we see in the direction of the galactic center, what is the origin? The 2 main hypotheses are the following. From one side, the galactic center is the region in which we expect to have the largest signal coming from dark matter clustering in our own Milky Way. And so one possibility is invoking the fact that we are looking to the first signal of dark matter annihilation in the galactic halo. But the inner galaxy is a pretty crowded place, also from the point of view of different stellar populations. And even if we have been modeling the stellar populations that we know, there might be a new stellar population of faint sources that we don't know yet. And this might be contributing to the observed signals, giving to us an excess with respect to our theoretical models. So the origin of this excess is pretty debated, but it's very important to sort it out, because, as I was saying, the characteristics of this excess look very similar to what we would expect to dark matter at first sight. But after a significant community effort and a debate, developing new methods, tackling the bias coming from the modeling of the background diffuse emission, we now are reaching an agreement for the fact that the bulk of the galactic center excess is likely from a stellar new population. And this is coming from the observation of the properties of the energy spectrum. For example, in this plot, you see the energy spectrum of the galactic center excess, which is measured up to tens of GeV. And the fact that we have an high energy tail extending up to tens of GeV is suggesting that we cannot explain this only with dark matter annihilation that will give to us at some point a cutoff, but is most likely explained by the inverse Compton emission of the particles that are emitted from those stellar population and are emitting with a similar mechanism with respect to the pulsar halos, also photons at those energies. And if we want to explain this high energy tail with dark matter, we indeed need more tuning. The morphology of the excess that was initially found to be compatible with a Navarro-Franke-White profile recently has been found to be more consistent with what we would expect from a distribution of stellar objects in the galactic bulge of the Milky Way. And this is coming from independent evidence coming from different groups. And the signature is a longitudinal asymmetry at around 10 degrees radius. And finally, we are detecting with photon count statistics methods a result point sources in the direction of the inner galaxy. And this is giving to us a possible hint from the tip of the iceberg of this new stellar population. And the number of sources of this new stellar population depends on the specific luminosity function, which is something that is under investigation. So all in all, those analyses recently corroborate at least partial stellar origin of the excess. And in order to sort out the origin of the excess, multi-wavelength searches for the stellar population that might be giving this excess are ongoing, because those sources might be unresolved in gamma rays, but still be detected at other energies, for example, in X-rays or in radio searches. And also, they can be giving a cumulative gravitational wave emission. And in final, if this signal is coming from dark matter, we would like to see a consistent signal elsewhere, for example, in the other astroparticle messengers, such as antiprotons or gamma rays. And at the moment, the region of the annihilation cross-section as a function of dark matter mass that is explaining the galactic center excess, this red dot, is tested, but not completely excluded by the gamma ray searches for signals in dwarf galaxies, is tested also by the antiproton constraints and is indeed excluded by the large Magellanic Cloud constraints obtained with radio emission observation. So this is an important future investigation for the complementarity. Passing to the outlook and some perspective on the observational point of view, we have currently important new telescopes that just started to take data. We have on the X-ray energy band the SRG Rosita, and in the TV energy band the LASO experiment that will give to us a complementary vision of the emissions that I've been describing to you in the X-ray band and in the multi-TV band. Forthcoming experiments are going to cover again the X-ray energy band with the Athena experiment, the CTA I've been mentioning many times covering the TV, and the bridging between the Fermi-Lat experiment and the ultra-energy gamma rays detected by LASO, OC, and S. And we are waiting for an antimatter experiment that is called GAPS that is going to measure the flux of antimatter particles, for example, in protons, but possibly also antideuterons. And I have some allied slides in the additional material. And we have also some dream project to have new telescopes, specifically in the X-rays, in the MEV energy band, in which we have a drop in sensitivity in the last few decades of experiments. And then also from the antimatter, we are developing some new ideas in order to have observations up to the TV scale. From the theoretical point of view, we need a better understanding of cosmic ray acceleration and propagation, because we need to go beyond the current phenomenological model in which we typically assume one source class and an isotropic transform model. We need to understand better the microphysics of acceleration and propagation, and this is needed at different scales. And whenever the uncertainties in those modelings or in the modelings of the interaction of astroparticles with the background are overwhelming, we need to have consistent statistical methods in order to include those uncertainties into our inference processes. And then we need to keep exploring new possible signals from sub-GeV and TV dark matter and new physics to reach out the possible signatures that can be explored with new forthcoming detector in those X-rays and TV energy bands. So multi-messenger wavelength target is again the key. And recently, also the astroparticle community has been starting to use massively machine learning and advanced statistical methods to fully exploit the data that we have. specifically with problems of classifications, emulation, and also inferencing. So to conclude, astroparticles are complementary messengers of fundamental physics and astrophysics. The data precision at the moment challenges our current and theoretical understanding, and many puzzles in new processes arise, as the two I've been discussing with you. And to shed light on current excesses, we need a multi-messenger wavelength target approach and also new forthcoming data. And those forthcoming observations will offer not only the opportunity to clarify the success, but unique opportunity to disclose the sub-GeV and TeV new fundamental physics and astrophysics. I thank you for the attention, and I invite you to have a look also to the highlights that have been inserted in the slides.